Here we have a torque problem with a ladder up against a vertical wall. So let's draw the ladder as a long, thin rod that makes an angle of 53 degrees with respect to the horizontal. So the length of the ladder is 8 meters long, and it's 22 kilograms. So we have the mass of the ladder times G is 22 times 9.8. Alright? It's leaning up against a vertical frictionless wall. Now when it says frictionless, what that means is that the wall force points perpendicular to the wall. So there's a normal force here, but there is no horizontal, or I guess there's no parallel component to the wall. There's only a perpendicular component. Now on the ground you have a perpendicular component like you have with the wall, but you also have a parallel component, which is the force of static friction, right, that's acting on the ladder. So it's important to understand what that means. When it says a frictionless or a smooth vertical wall, that means that the only wall force is this force that's perpendicular to the wall. And that's going to be important for figuring out the angle for the torque. We also have a 92 kilogram person climbing the ladder at some distance above, some distance. We don't know how far up the ladder. And the ladder is just about to slip, which means that we can say that the force of static friction is mu sub s times the normal force, because it's just about to slip. It's at a, one of those threshold values. So the other forces, I've drawn 3 of the forces on the ladder. The other 2 forces are the weight of the ladder, which is halfway up the ladder, and then the person. I don't know how far up the person is on the ladder. I'll just draw him up here. I mean, for all I know, the person's down here somewhere, at this point. But I'll draw it up here. Okay. So I think I've got all the forces. Okay, so gravity, there's no tension. I've got the normal forces in here, the force from the wall and the normal force from the ground. Let's see, there's no applied force. I got friction here on the ground, static friction. There's no spring force, there's no centrifugal force, there's no buoyancy. So that's my whole checklist. So I'm ready to write down my static equilibrium equations. The first one is that the sum of all x forces is the force of static friction minus the wall force. That's equal to 0, right? Because our sign conventions, of course, our standard Cartesian sign conventions work like that. So the force of static friction and the wall force are the only 2 forces that have x components. The static friction is positive, and of course it can be written as mu sub s times the normal force. Okay, nothing we can do with that for now, so let's look at the y forces. Now there are 3 forces that have y components. There's the normal force, there's the ladder's weight, and the person's weight, and those sum to 0. Now I can actually solve for the normal force, right? The normal force is 1117.2, right? If I add up this plus this, I get the normal force. You know what? I have the wall force too if I want it, now that I'm looking at it, because now I know the normal force, and I'm given mu sub s is 0.61. So, heck, I might as well. The wall force is, from this equation, the wall force is 0.61 times the normal force, and that's 681.5. Okay. I have a feeling I'm going to need those, at least one of those, so might as well solve for them now. Okay, so now let's look at the torques. So I'm going to, my typical sign convention is that I stick the pivot at a place where there are unknowns. Now actually neither one of these is an unknown, but I got 2 forces there, and I don't want to if I put the torque somewhere else, then I'm going to have to deal with the torque of these 2 forces. So I'll put the torque down there at the bottom. So, sum of all torques. Torque due to the ladder's weight, plus the torque due to the person's weight, plus the torque due to the wall force. Those sum to 0. Now the torque due to the ladder's weight, the ladder's weight is trying to make the ladder rotate clockwise, so we have a minus sign. The distance from the pivot to the point of application of force is 4, halfway up the ladder, because the ladder is uniform. It doesn't say that the ladder is uniform, but I think we can assume that. Let's see, the weight of the ladder is 22 times 9.8. And then sine what? Okay, so the r vector is here. That's the r vector for the ladder. So we've got to figure out this angle right here. Now, if this is a horizontal line, then I know that the gravity is vertical, so this part is 90 degrees, and I know that the ladder makes an angle of 53 degrees with respect to the horizontal. So if I add those two up, I get 143. There are other ways to get that, but I think that's the easiest. Alright, so that works out to be minus 519. Now, the torque due to the person, that's minus. I don't know the distance that the person is up the ladder, so I'm going to treat that as an unknown. Weight of the person, and sine 143 again. Same logic applies for this angle that applied for the ladder's angle. So that's minus 542.6x. And then finally, we have the torque due to the wall. Now that's positive, and the distance from the pivot to the point of application of force is the entire length of the ladder, which is 8. We multiply that by the wall force, which we know is 681.5. Sine of what? Alright, so let's see. The r vector for the wall points that way, okay? And I know that this angle is 53 degrees. So that makes this angle 180 minus 53, right? Because these two angles have to add up to 180. So 180 minus 53 is 127. Again, there are other ways to calculate that angle, but that works for me. That's 4,354.2. Okay, so my torque equation then is this. Minus 519 plus 542.6x plus 4354.2 equals 0. So that's 3835.2 is equal to 542.6x. X is equal to 7.1 meters. So that's how far the person went up the ladder.